called Super Kamiokande. It's in Japan. And in some sense, it's an unbelievably fantastic experiment that's been put together in the last decades. First is a version that was called Kamiokande, then Super Kamiokande. Kamiokande is named after a mountain in Japan, and this is an experiment that's done under the mountain in Japan called Super Kamiokande. And as often seems to happen in physics, is you build something very ambitious to do some new physics, and you think you know what you're doing, and then it turns out that what you end up doing with a powerful instrument is something quite different than that. And this story follows that. And that is the original purpose of this experiment that I'm going to show you was something I alluded to just before the break. And I said that in order for us to, rightly or wrongly, but our best ideas right now for how to explain somehow that we end up with a matter-dominated universe, what we live in now, when everything we know about nature in the early universe should have created as much antimatter as matter, and then it annihilates each other, and we wouldn't be here. That there's some asymmetry that existed in the early universe that we don't understand. We're not able to make a good theory of it. I'll come back to this in a future lecture. But we have narrowed down some features that we think have to be there in order for there to be this asymmetry, for there to have been this asymmetry in the Big Bang that enabled us to be here as matter now. And one of those is what I call the CP violation, which is whether when you have a symmetry, whether a neutrino, if you look at it one way or another, has an asymmetry in it, which we haven't quite come to yet, but it's the goal when I talk about the goals of the next 10 years. The second one is something I mentioned, which is that the proton itself has to be unstable. So these are the two features that scientists believe have to be true in order for us to find a way to explain how we end up with a matter-dominated universe today. So a big effort was made to try to see if protons actually decay. And the decay mode that was picked is the one that I show here. There's other possible ways that it would decay, but the one that I show here is that you start with a proton, and it decays and makes an electron of the same charge and a pi zero. So the Japanese and collaborators decided to build the most ambitious possible attempt to see if protons decay. And instead they found the fancy words that I'd use are lepton number violation, but that's a different way of saying that neutrinos change their identity, or we have neutrino oscillations. That it broke a rule that these particles are all in their own families that actually talks to each other. So they made a totally different discovery, and this experiment is the one that made that beautiful image of the sun that I showed you. This is what it looks like. So it is a huge vat of the purest water in the world. By purest water, I mean they have a particular method of taking the water and purifying it by something called reverse osmosis is the technique. And if you go there, I've been there, and you go inside, one of the things the Japanese love to do is to let you taste this purest water in the world. So you get to drink this water. Of course, it tastes like water. But, it basically is what they use. And it's got to be very pure because they build this huge tank, and you don't want anything that prevents you from being able to really see as clearly as is possible through the water to be able to see anything that happens in the water. What's shown here in these little dots, I'm going to show them to you, are all, you have to imagine, is just like big eyes. They're photosensors that are looking at the volume that's filled with water. So this is completely surrounded with just photosensitive devices that look at it. This is a picture of it from inside when it was being filled. So you can see the liquid's up to this level. The picture's somewhat distorted, but the photo tubes are shown up here. There's some people in it, so you can see kind of the size of it here. And the water itself is the target, and it's the detector medium. You need roughly 50,000 tons of pure water in this. And it's, for size, 41 meters high and 40 meters in diameter. So the size of it is just enormous. They identify all the particles that might come out if a proton decays. So the way they made it, an electron, or maybe a muon, or neutral pions that we've talked about. And they do that by what's called Cherenkov radiation. I talked a little bit about Cherenkov radiation when I talked about particle detectors, but this is a particle, charged particle, going through a medium at faster than the speed of light in that medium. And then it makes a ring, which we call a Cherenkov ring. And that's what they use as primary way to see the particles, identify them, and by looking at the ring itself and the size of the ring by measuring what the particle was. Then they reject all the backgrounds that they don't care about, from cosmic rays or natural radiation, from the fact that rocks have radioactivity that built into them. And it's 1,000 meters underground in this mine in Japan. So that's the detector. And it was used and has been used first to see the solar neutrinos, but now I'm going to go on and talk about neutrinos that come from other sources, and in particular, the neutrinos that come about from the fact that high-energy cosmic rays hit the top of the atmosphere, make secondary particles, and some of those decay and give neutrinos. We give that a name. We call it atmospheric neutrinos. I've been talking the last hour or so about what we call solar neutrinos, neutrinos that come out of the sun. Now I'm going to talk about atmospheric neutrinos. They're different energy, and there's different things that we've learned using atmospheric neutrinos. If you remember, the neutrinos from the sun are all electron neutrinos because they were associated with beta decays that give electron neutrinos. In the atmosphere, we basically have cosmic rays that come from somewhere outside the atmosphere. They come into the atmosphere, and when they come in, they interact by hitting some sort of matter, some proton or something, and they make secondary particles. Shown here, making neutral pions that make photons and electrons, are charged pions, some that decay, but a lot of these give as a final product neutrinos. This is a muon neutrino. We have electron neutrinos that come by the decay of muons, and so forth. And so we can quickly do a calculation of what all these modes are, and fairly accurately what you expect is that the number of neutrinos that you detect that are the type like a muon should be twice the number that are associated with electrons. So when the neutrino interacts, the ones that make muons will be there twice as often as the others. Okay, so what is actually seen is the following. If you take the picture of the Earth that I have here, and somehow cosmic rays from somewhere in space coming and interacting and making neutrinos, then we can observe neutrino, and our device is in the Earth somewhere. I've drawn it right here. So it's under a mountain here, but it's a long ways going the other way. Then the neutrinos come in this way, they come in this way, they come in all different angles. If I measure it as a function of a length over the energy of the neutrino, it's just what I've picked as a form here. The electron neutrinos are pretty much independent of where they come from, but the muon neutrinos look like this. This was a puzzle. It's basically a result of neutrino oscillations, and taking the formulas that I showed you, I can then fit this and measure the fact that the path length was different for the neutrinos that came this way than it was for the ones that came this way, and they changed their identity. And that won a Nobel Prize for the first time for the Japanese, Toshiba, by seeing for the first time that neutrinos actually oscillate. So this was the evidence that they oscillate. And drawing the picture here, I'm going to point out just for completeness that there's another phenomenon that complicates the issue even more. But if we have a detector that sits on the Earth, and it's here, just under the ground, and it's measuring neutrinos from wherever they come from. And so I can compare up ones versus down ones. And in the case of this experiment, it came out that there were half as many going up as going down. And that's shown in the data here as a function of angle. If you calculate what you'd expect, if nothing happened for them to disappear, it would follow this line here. But the data is here. It agrees going down, but going up, it's reduced. So trying to explain all that, they actually realized that there's another effect, which I'm only going to mention because for completeness today, and that is there's an effect of neutrinos that complicates everything I've said so far, which is that they have a special effect going through matter. And so when the neutrinos come one direction and have to go through the whole Earth to get to the detector, there's actually an effect called matter effect. It's named after these three gentlemen here, Mikheyev, Smirnov, and Wolfenstein, and it's called the MSW effect. That's, of course, detectable easily by comparing what neutrinos you see at night compared to daytime. So if you look in the daytime, the neutrinos are coming straight at you and otherwise the other way. So that's the way it's done. And there's a whole phenomenology, which I'm not going to build up here, for the kind of enhancement that you get. It's like a phenomenon that some of you may know or have heard of called birefringence, and in a medium. And this is a big effect, actually, in these neutrino experiments, so it has to be taken into. So I only mention it really for completeness. There's basically an index of refraction. You can go through, there's a whole series of papers that measure this effect. It's not telling us anything special about what I was trying to get at, which is the neutrinos, their mass, and so forth. But it's a phenomenon that happens, a physics phenomenon, which is very prevalent in the literature. So we have basically these complication of the matter effects and then the neutrinos that come in and changing from one to the other. My notes give pretty much what the background is of these. Light, more or less, the number of muons that change into tau leptons is consistent with the mass for the atmospheric neutrinos of approximately 10 to the minus 3 eV squared. And there was an angle that I always had, and that angle is near maximal. In other words, even though I put it in an angle, that angle actually turns out to be almost maximal. And as I say, you can see this in my notes. So we end up, in the end, being able to characterize neutrino oscillations by some areas in a space that on one axis is masses, or mass squared, and on the other one is this angle. And somewhere gives a good measurements of where we know things are. Theoretically, we don't have any way to expect it to be somewhere. We're actually determining these parameters, which come about depending on the various parameters that I talked about, and the one we care about most, of course, is the relative masses of these neutrinos. Okay. So that experiment was a fantastic experiment. It saw the neutrino oscillations. But we still haven't resolved, for sure, the whole problem of the sun in a way that's satisfactory. And that got done by taking that experiment that I just showed you and adding it to another experiment that was being done in Canada called Sudbury. Sudbury is a big caldera that is a nickel mine, and in this nickel mine, the Canadians, Americans, and British built an experiment to also look at neutrino oscillations, but in a somewhat different way. And this experiment took advantage of the fact that in Canada, they have stored the biggest volume of what's called heavy water. Heavy water, water's H2O, we all know, but there's also water that could be D2O, and D2O is the valuable fuel for a particular kind of nuclear reactor that people thought was going to be the dominant nuclear reactor at one point. And the Canadians stored a huge amount of D2O, heavy water, in their government facility that has basically atomic energy. So they happen to have the resource. And it was realized, I'll come to a picture of him, I have it in a different slide, by a physicist that was at University of California, Irvine, that using D2O instead of H2O, the combination of the two could resolve the unknown parts of neutrino oscillations and this mass difference question, because you can see the modes that you couldn't see in the hydrogen case. So it was proposed to the Canadian government to borrow 1,000 tons of D2O from the Canadian government and put it into a deep mine where they mine nickel actively in a special detector. This is a picture of the detector. In contrast to the one I showed you in Japan, which is the biggest volume in the world, this is somewhat smaller because D2O is so valuable. This is made like a sphere. So it's a spherical volume full of heavy water, 1,000 tons of heavy water. And that heavy water is surrounded by detectors and regular water in order to see anything that happens externally, so they can look internally at interactions that actually happen internally. And this is done in Canada. I've written down here the different reactions that can happen. There's the reaction of a neutrino at the very top, scattering off deuterium and making an electron and 2 protons, or the neutrino scattering off the neutron and making an electron and a proton. And only electron neutrinos can cause that reaction. So that is available because the deuterium has neutrons. When we had regular hydrogen, regular water, we didn't have neutrons. The neutral current reaction, you remember we had neutral current and charge current kinds of reactions when we talked about the way particles interact, and the particle that carried the neutral current reaction was called the Z0, and we talked about the discovery of that. The neutral current reaction is one that doesn't change charge from the initial state to the final state, and so you have the neutrino on any one of the neutrinos hitting deuterium and just making a proton and a neutron without creating a charged particle along the way. And deuterium has twice as many nucleons as hydrogen, and so as water. And so all the neutrino families contribute equally in this case. And there's an energy threshold that you have to take into account that's 2.2 MeV. So you can take also just elastic scattering, the last thing that can happen. And that is the neutrino comes in and doesn't scatter off the deuterium or the proton or the neutron, but off an electron, and that's also measured. So the bottom is the 3 things that they measure. Charge current reaction, where basically you change charge between the initial state and final state. The neutral current reaction, where you basically just scatter, and scattering off the electron itself. They also measure, for completeness, something called the boron 8 flux, and that allows them to kind of standardize it with what you expect from this model of the sun. So, going back to this prediction of all the neutrinos that come from the sun, using heavy water, you're able to distinguish all these parts. The three different colors are the three different measurements from snow from this experiment, and they come together at a point. They make a measurement, 3.41 plus or minus 0.45, and it provides 5 sigma, which is the magic number, evidence for what we call neutrino flavor mixing, that is, neutrino oscillations itself, and the total flux for the first time agrees with this puzzle that I talked about, the solar neutrino puzzle. So let me show you that, skipping a couple slides here, wherever I have it. I think. This is just some pictures of these reactions, and this is what they measure. So they measure 3 numbers very accurately, and the total number of neutrinos is much more than the neutrino electrons. So when I showed you the first puzzle, it's that we expected neutrinos to be at some level here. And all the early experiments I showed you, gallium, chlorine, and so forth, were all down here. This experiment that sees all the different modes measures all the 3 modes. And when you put it together, it comes up and describes exactly the right number of neutrinos to match the predictions of the burning of the sun. So the problem of the nuclear physics is not there. It appears fine. And the only problem now is to understand quantitatively the problem of neutrino oscillations itself. And so the neutrino oscillations are studied in this reaction, as I said, and now what they've done is, as all these experiments get more sophisticated, is what was done at the beginning, everything I've shown you so far was with pure heavy water. Now they've added salt to the mixture, and that gives them the ability to add neutral current detection, and they go back and forth between they can take the salt out, pure salt and no salt, and in this constrained and unconstrained way, they basically have been able to definitively go back and forth between the neutrino oscillations and determine the numbers. This is truly a beautiful experiment. And finally, the combination of this and the Japanese experiment definitively indicated that the neutrino flux coming from the sun contains muon neutrinos by the time it gets here, and that supported, and actually quantitatively, this whole picture of neutrino oscillations. And this was the picture showing it all together. And 4 years ago, I guess, the Nobel Prize was given in physics for this. So this is rather recent. And this experiment continues in some of the form that I told you, mostly doing the salt and so forth. So the detailed features of the neutrino oscillations can be measured. Now, before we close today, I want to introduce the fact that we now are moving into a more controlled, something physicists always need to do, a situation where we can control the variables better. So everything I've shown you so far, we've used nature to be a source of neutrinos, either from cosmos, from the sun, from a supernova, from something else. If we really want to control things and understand neutrino oscillations well, then what we have to do is to be able to control a problem, control the energy, control the direction, control everything we can. As you do in experimental physics, you want to control all the variables. The goals, I would say the 2 big goals are 3 goals maybe. Are the third one being, are there more than 3 neutrinos? Is there what we call sterile neutrinos, extra neutrinos? that, as I pointed out, is an unresolved problem. In terms of the neutrino oscillations, we've now seen those. And now to pursue those, the goal is to understand whether the hierarchy, the ordering of the neutrino masses, is the same as the ordering of the quark masses or inverted. That may seem like a little problem, but it turns out to make a substantial difference theoretically. And the third problem, maybe the ultimate one that these experiments want to do, is see whether there's any asymmetry in neutrinos, what we call CP violation. And that, as I said, relates to whether or not neutrinos behave in a way that help us maybe have a clue for how the early universe became matter-dominated. So that's the goal. A way to do this, in the first place it was done, was again in Japan. So in Japan, they took not just this big detector, which you can see kind of symbolically here, looks like the picture that I showed you, detecting neutrinos that come from either the atmosphere or come from the sun. I've shown you two kinds. But instead, from a particle accelerator. So what they did is go to the laboratory in Japan where they have a big particle accelerator. Not as big as CERN, but a big particle accelerator. And that is shown in this picture here as the KEK laboratory. It's here on a map of Japan. And the detector is in the mountains in the eastern part of Japan where it's very mountainous and where they're skiing, and in the mountains some mines, and this is in a mine basically built into a mountain. So what they did then is build a beam of first protons, let the protons hit a target and make secondary particles that have finite lifetime, ions primarily, but also k-mesons, and aim that beam toward this detector across the other side of Japan. And that experiment is still running, of course, was put together starting maybe 5 or 10 years ago, and so what I'm showing you is fairly recent. Doing that, they were able to see neutrino oscillations, which I show here, using terrestrial man-made neutrinos and not just trying to explain something about the sun or something about neutrinos coming in the atmosphere. And this result is consistent with the ones before and potentially much more accurate, because you can control the energies of the beam, the directions of the beam, measure backgrounds better, and so forth. So this is a picture of this experiment sending a beam of particles along what we call long baseline, hundreds of kilometers from the KEK laboratory across Japan to this detector in the mountains of Japan. And when a particle goes through, it makes Cherenkov radiation. The energy of the particle creates a certain angle. This is the sum of many interactions, but you can see that it makes a circle like you expect from this Cherenkov radiation. The direction of the circle is marked by a little diamond on here, but basically you can point back from these back to where the origin is, and it's all very beautiful. Changing the energy of the machine is equivalent to changing the length that it has to decay, and so they measure the number of events that way. And they were able to rule out in very early running, that's shown here, the probability that there aren't any oscillations. There has to be oscillations from even the very early data that they got that they can control very well. And measure the parameters. So this is the same plot with parameters that you'll find in my slides, where this is the angle, that angle that I used when I drew the formulas, and the change of the difference in mass between the two. And these are just the different measurements. So they're all consistent with each other, and they're able to measure the disappearance into this allowed region. So they confirm in this terrestrial experiment the same result and the same conclusion that was gotten using neutrinos that came naturally in the atmosphere, and neutrinos being made in the atmosphere from cosmic rays striking the atmosphere. This is just, again, the limit on these, and the details of what this looks like are more interesting to me than to you. So, in summary, the first detection of the accelerator-produced neutrinos were 250 kilometers away. They confirmed that neutrinos that start as a muon disappear along the way, and they're able to actually parameterize that disappearance with the same parameters, this angle and mass difference that we had when we looked at neutrinos, natural neutrinos from the sun and from the atmosphere. The second one, man-made, is done at Fermilab in Chicago, and there they start at Fermilab and they send the beam to a mine that's in Minnesota called the Sudan mine. And this experiment was the first attempt. I'll show you next week the next generation experiment, which is very ambitious, to make a man-made neutrino beam other than the one in Japan. And the experiment was called MINOS. And so the idea is to take Fermilab, make very high energy protons, have those strike a target, have a region where the products of that pass through space. As they pass through space, they decay and make neutrinos. This is just some of the apparatus. The distance from Fermilab to the Sudan mine is 700 kilometers, 735 kilometers. In 735 kilometers, the Earth curves quite a lot. So they actually have to send the beam of particles down at an angle through the Earth, so they emerge again at this detector. I've shown that here. So I've exaggerated it a little bit, but the Earth curves, so you send particles down and they emerge out where you actually are detecting them at the Sudan mine. The actual deepest point for these neutrinos that are traveling about 735 kilometers is 10 kilometers below ground. That's how much the ground is there. So none of the farmers or anyone along the way has to worry about the neutrinos. The same is true here in Italy, where in a different way, neutrinos have been, for a different purpose, neutrinos have been sent from CERN to the Gran Sasso laboratory. And again, that path is all underground. So you don't have to worry about radiation, not that neutrinos are going to radiate, but they basically travel completely underground. So this experiment was put together to go from Fermilab to there. This is making the neutrino beam itself. So the neutrino beam is created by taking protons from the accelerator itself, running them into a target, and taking a a pulsed electric device that has fields, electric fields, that will focus the particles forward. So normally, if I have a collision, particles go out in all directions, but you want to gather as many of those as possible toward this apparatus that's 700 kilometers away, and you can design a special device that has electric fields that bend the particles, so all the particles, however they were produced, are aiming toward this detector far away. To do it in a sophisticated way, they actually have two of them, one following another to correct for it. So photons come from the machine. They interact, they make secondary particles. The secondary particles are pi mesons, k mesons. They're unstable, they decay. Show them decaying along in here. So then they make a decay path, which in this case is about, I have it here, 675 meters. And in that 675 meters, we've now taken the particles and aimed them all down that, aiming down into the ground, but to come out somewhere else. They're not going to go anywhere. They're charged particles. But because their lifetime is finite, some of them decay along the way. So a pion is shown here, decaying into a muon and neutrino. By the time I get to the end of this, I have then a shielding wall, or dirt, and basically the particles are all absorbed except for neutrinos. So you have coming out of this finally just neutrinos that go through 700 kilometers of dirt and then eventually enter into the detector that's able to see those. And this just shows a picture of the neutrino spectrum that you get depending on how you set the conditions of this apparatus. So you're able, and as I said, the difference between and the motivation or why you want to do this kind of thing on an accelerator instead of nature giving the neutrinos as we've done before is that I can choose to do what I want. So I can make neutrinos that look like this in energy, or I can get it like this in energy, or even like this. So I can run with different configurations where I know something about the neutrinos, where they're coming from, what their energy is, what kind of neutrino they were when they started, and so forth, which makes it much simpler to try to interpret an experiment that we use. So this is a result then from this terrestrial experiment, which is that looking at it as a function of the energy of the neutrino, this is what is seen, where you expect the data to follow this black line, which is what you get using the parameters of neutrino oscillations, which are shown over in the right. So we had this angle, and the biggest an angle can be is 1, and that's where the data is. It could have been here or somewhere else. So we learned that this mixing angle is maximal and that have a particular difference in mass. So we have difference in mass in some units here, which I use as EV squared over C squared, where the different answers for different experimental configurations are all in here, but this tells us a difference in mass. So what we've learned from atmospheric neutrinos is shown here. The difference in mass is something like 10 to the minus 3 EV squared. That's the difference between two of these neutrinos, not knowing what the mass is, but what the difference in mass is. So what we have is a picture that looks something like this. This is where we are basically today. We have three mass states, nu1, nu2, nu3. I've shown it in this order, and I've shown different shadings depending on how much of it is nu-e compared to nu-mu to nu-tau. And this is the best we have fitting the data that we have now. And I've put in all the details here, which is in the slides. And you'll see that the information comes from everywhere kind of put together. That is, if you look up here, we bounded the amount of this by reactor experiments. We know this from the atmospheric experiments. So all these different experiments give us different pieces. I've kind of tried to summarize it in one slide here, but this is the picture we have, these three masses. We don't yet know if this is the bottom one, first, whether this is the right hierarchy or it could be the other way around. And secondly, we don't know how far this is above 0, or if it's at 0. We don't know the lowest one, what its mass is. And I'm going to talk next time about the experiment to determine that. That's the best one that people have done. So let's look at the numbers a little bit. For solar neutrinos, every second there's 2 10 to the 38th solar neutrinos produced. Almost all of them get out of the sun. And that's because they weakly interact with matter. So this is the number of neutrinos that come out of the sun. Traveling very nearly the speed of light, it's 8 minutes travel time to get to the Earth. So it takes 8 minutes for these neutrinos to get to the Earth. That's how many there are. 70 billion neutrinos per second then come in each square centimeter path of the Earth. So here we have 70 billion neutrinos per second in each square centimeter coming through us. And the idea is to catch these neutrinos to see what they tell us about the solar interior. And we basically now can make a convincing case that there's this neutrino oscillations. That is, whether we make man-made neutrinos or we take neutrinos from the sun, we get the same conclusion. So we haven't somehow just tried to solve a problem that we didn't have the right number of neutrinos from the sun and made a consistent picture, but we can actually totally independently create our own neutrinos and see with the same parameters the neutrino interaction. This is the experiment that's being done to use neutrinos in the second way. I'm going to talk more about this next time, called CAMLAN, that looks at neutrinos not from a particle accelerator that I showed you, but from a particle reactor. And that has been done to some extent already. And first, the neutrino parameters from a solar experiment give you, again, in this space of mass difference squared compared to this angle that is well known. The experiments that are looking at the reactor experiments, the primary one that's been so productive is called Daya Bay. It's not so far from Hong Kong, in a bay in China where it's surrounded by several reactors. And using the neutrinos that are detected from these reactors has enabled measuring these measurements. It's not the only one, so as we do otherwise in physics, there's one in Korea, which is shown here, different domes or the different reactors, and one in France called Double Shoes. It's called double because there's two reactors. All of those have been giving information on this particular angle, theta 1,3. Why do we care about theta 1,3? It's an unknown angle. I'll talk about it some in the future. It has to be finite. We don't know yet. If we're going to have CP violation for neutrinos, something I alluded to as a condition, we think, for explaining why we live in a matter-dominated universe. So for neutrinos, we want to measure whether there's CP violation. We're not ready to do that yet. It's probably 10 years away. But before that, there's a condition that has to be there in order for there to be CP violation, and that is a parameter that we can measure has to be finite, meaning not zero. So far, we don't know. And these experiments are trying to do that, and I'll talk about it a little bit more next time. If I want to show anything else today, I'm out of time. As a preview, see this big picture here? I'll talk about it later, this huge thing going through this village, and this is the big device that I'll talk about that's destined, we hope, to actually measure finally the mass of a neutrino. We've never measured, I've talked about mass differences, but not the mass of a neutrino. That's done, and I'm going to talk about it next time by looking at the endpoint of tritium beta decay, where if the mass is zero, it would go out to here. If the mass is finite, it'll cut off somewhat earlier, and you have to measure this extremely accurately, and it takes a huge and very complex experimental setup to do that, which we'll talk about next time. So that's all for today. Thanks.